Okay, a natural presentation. Did anybody pick the pun? I when um when Billy and I
But you
were
don't like
organizing,
puns.
pardon? Yeah, I know, I was literally about to say that. So when Billy and I were organizing this course, we spent about the it took us about an extra month in order to get the ball rolling, basically purely because we were stuck on the name. And we kept coming up with names, but they were all puns. And the problem was I was vetoing every single pun. So I believe that some of the most obviously some of the most clever people I've ever met have been mathematicians. But it seems like that intelligence really maps over to wit when applied to the mathematical presentations themselves. I mean, I've met mathematicians who are incredibly witty and incredibly funny, but they seem to want to name everything after puns. And so I vetoed puns, and then here I am on my third name, and I've already resorted to puns. But mind you, I guess technically speaking, it's not a pun. So today's lecture is about naturality in one part, but then on the second half, we're going to do our first bit in this course about presenting mathematics itself, right? So, yeah, do you see? So, how do you present and make it sound natural? But then also, we're doing the problem is you've got this. So, another name that I came up with was, uh, what was it? Like naturality. Yeah, presenting, and then where do you have to put the brackets? Yeah, I wanted to like,
Yeah, I
no,
don't
it's
think
not
it's
there.
possible between the
Yeah,
let's see.
it's not possible because you need this extra L in here. So I don't know if you put square brackets or something.
How
But anyway,
about how
so
about
the point.
rhetorical transformation?
Yeah, that's not bad. Hey, I was convinced that there was some clever way to do it. You see, the problem is in one instance, he wants the noun, uh, what is it? Naturality. I guess that's also an adjective. I don't know, but you've got natural, the adjective. You've got natural versus naturality, and it turned out to not be so easy to make a pun out of that. So, anyway, I worked very hard in order to become what I hate and present a lecture titled after a pun slash play on words. But that's my introduction for today. We're going to be discussing the mathematical concept of naturality, and then later we're going to be talking a little bit about presenting mathematics. Okay? All right. So in lecture number one, I spoke about making subtle ideas apparent, and I spoke about motivating a theoretical idea from many different avenues. So you can, in the first lecture, I tried to motivate category theory from a logician's point of view, from a computer scientist's point of view, and also from a mathematician's point of view. And the mathematician's point of view that I gave was this idea of find an idea which is subtle and make it apparent using mathematics. Okay, and what I really had inside my head when I was presenting that was the concept of naturality. So I presented two maps, which I'm going to present again today, involving vector spaces and their duals. And I suggested that there was a difference between the two of them. And I didn't have the language at that point in time, but I was really saying that one of them is natural and the other one is not natural. And so we're going to explore this idea more formally today, and we're going to write out the proper definition and then look at it and see why this is a reasonable piece of mathematics to write down. Okay, so let's start off with the definition. Let f from C to D. Wait, I need a G as well. That's not in the notes for some reason. Be a pair of functors. A natural transformation denoted eta from F to G so we've got these two categories, C and D. It is a D-indexed, no, sorry, C-indexed. It is a C-indexed collection of morphisms inside D.
Sorry, can you rewrite the FG at the top?
Yeah. Okay.
Thanks.
No worries. Okay, and so what I mean by that is for every object C inside the category C, we have a morphism inside the category D, and these are going to be subject to a condition. Right? So for every object C inside C, we have two objects inside D. We've got f of C and we've got g of C. And the morphisms eta sub C are to go from f of C to g of C. And if you notice, we haven't used all of the structure of a category yet. So the category C has got these objects which parameterize this collection of morphisms inside D, but there's more structure than that. There are also morphisms inside C, and the naturality condition is going to ask that these morphisms eta sub C are compatible with the morphisms inside C. And this is possibly the first time in this course that we've seen the language that I'm about to use. So I'm going to say, then the following diagram commutes. And then I'll explain what that means. Okay, and so what that simply means is we've got a source FC here, and then two different ways to get down to the target G of C prime. We have this composite, and we also have this composite. To ask for this diagram to commute is simply to ask for those two composites to be equal to each other. So IA eta C prime composed with f of f is equal to G of f composed with eta sub C. And that's for all C inside C. Right, so if you imagined that we were inside maybe the category of rings or something, and all of these maps were multiplication maps. So maybe this was multiplication by an element A, and that was multiplication by an element B. And here this is multiplication by B followed by multiplication by A. Then the two ways around the square are to multiply by A and then B, and the other direction is to multiply by B then A. Sorry, am I in the way? Oh, yeah. Okay, so I'm just motivating the language commutativity of a diagram here. So going in this direction is to first multiply by A and then B, and to go in this direction is multiply by B and then A. And to ask for these to be equal is to ask for A times B to equal B times A. So that is to say that those two elements commute, right? That motivates the language of this diagram commuting. So that's where that comes from. Okay, and we can look at an example. So let me move over here. So as a very simple example, we'll look at what is called the opposite group. So suppose that we have a group in our hands. we define the opposite group G star to consist of the same underlying set as the underlying set of G, but multiplication is kind of via the inverse elements. So to make that precise, we write down this formula. So G1 inside the opposite group multiplied by G2 inside the opposite group is G2 inverse multiplied by G1 inverse, where the multiplication on the right-hand side occurs inside the group G. Okay, so I haven't written down any functors or collections of morphisms yet, so there's no relevancy of naturality yet. I've just introduced such a thing, such a concept, the opposite group to a group. And so now let me define a pair of functors. So we can just take the identity functor, which goes from the category of groups to the category of groups. And it acts identically. It sends a group to itself and it sends a morphism to itself. And then there's also, I suppose, the opposite functor, which also goes from the category of groups to the category of groups. But this maps a group G to its opposite group. And then on morphisms, so group homomorphisms, it actually just maps identically. So morphism F is sent to a morphism F. Okay, and now I can define the natural map from G to its opposite. So what I do is I say define eta to be the collection of morphisms from a group to its opposite, where eta, let me write it underneath, eta sub G of an element G inside capital G is equal to G inverse, and this is given G is an element of a category of groups. So that's a collection of morphisms, and I claim that this is natural, and to prove that, we consider an arbitrary morphism F from G to H, and then we need to consider the following diagram. So we apply the identity functor to G, and we get G, the identity functor to H, and we get H, and then the opposite functor to H, and the opposite functor to G, and then we do the same thing on the morphisms. So we have F here, and we have F here as well. Well, F star, but F star is just the identity as per what I wrote earlier. So maybe I will just get rid of that star. And then eta sub G and eta sub H. And then I claim that this diagram commutes. It's a simple calculation. I'll do it over on the left here. So am I in the way? No. Let G be an element of
Well, I think you made a mistake. The opposite multiplication reverses the order, but it doesn't put inverses on the elements. I mean, you could define a category a group that way, but it doesn't quite fit with what you're about to say. Don't you mean G1, the opposite multiplication with G2, is just in the reverse order? That's the more usual. That's the opposite category, right?
Yeah, that's the opposite category. You're right. So
just that
what happens in
if you do the calculation, you'll maybe just go ahead and do it. I think it'll turn out it won't work if you've got those inverses in the definition.
Okay, so if I did F star of eta G of G, then I get F star. So I've said this is G inverse, which is F of G inverse, which is eta H of F of G. So maybe that works, but maybe I don't have a homomorphism or something. Is that what might end up happening? So let's see. So let's okay, maybe that's how that mistake slipped in. So naturality seems to be fine, but do I not have a homomorphism or something? So eta, or do I not have a functor or something?
No, just check whether it's a homomorphism or not. Maybe do the calculation on the other board. It's instructive, even if it doesn't work.
Yeah. Okay. So is eta G.
Wait, are you implicitly using that it's a homomorphism on the previous board when you go to, like, what are you doing when you do f star of G inverse equals f of G inverse? Like, what is that?
Yeah, so I'm using it that it's a homomorphism there. So that calculation won't hold if this is not a homomorphism.
Right, okay, yeah.
So
the drama, the suspense, this is high-grade entertainment right here.
I'm glad to hear it. But hang on, this looks good, doesn't it? G2 inverse, G1 inverse equals, okay, because that's A to G2 multiplied by A to G1. Okay, so this is important, so let me make it clearer. So that's a 2 and that's a 1. But then that seems to be
I think it's confusing to use the same dot for a different operation, and you've changed the names of the elements. This is not the usual way people write this down.
Right.
So just keep the same name for the elements. So I would write G1 and G2, not G1 op and G2 op on the previous board. But change the operation to like dot with a circle or something.
Okay.
And then it'll...
Yeah, and also this bottom line is incorrect anyway. So I want to correct the previous board. I don't want the previous board to have the ops inside it. So I'm coming back to the first board and getting rid of those ops. I'm going to turn this into a circle so that we can see the difference between them. Moving back to the right board, let G1 and G2 be an element of G star, and then eta G of G1 dot G2 equals G1 dot G2 inverse, which equals G2 inverse dot G1 inverse equals...
You just did this calculation. Why are you doing it again?
So I wasn't happy with the last line because I need this to be eta
so keep it as...
Yeah, but that looks good, doesn't it?
Yeah.
That looks true.
That's right.
So we have a homomorphism.
Yeah, but not according to the definition you wrote over there. So write out exactly what circle... I mean, that equality you wrote down is fine by my definition, but not by yours.
So what I wrote is G1 circle G2.
Your definition introduces an extra inverse. So now calculate what eta...
Yeah, I can see.
Yeah.
Okay, so this equality does not hold. So the point is eta G of G1 equals G1 inverse. Eta G of G2 equals G2 of inverse. And so eta G of G1 and then circle eta G of G2 is going to end up being G2 inverse multiplied by G1 inverse, which equals G2 dot G1. Okay, and this is not what we want. So this is not equal to this. Okay, so that is the problem, and the solution is define G1 circle G2 to be equal to G2 dot G1 inside the normal group. Not the normal group, inside the original group. Okay, do we agree that all makes sense now? So I need to like, yeah, flag this. So wrong. Cool. Okay, and now everything's fixed. Okay, and so we have a genuine collection of homomorphisms now, and we have a yeah. Let me check the naturality calculation. Did I implicitly use? Oh no, it just doesn't. Yeah, there's no multiplication involved in the naturality condition proof. So this down here is fine. That's correct. And the new definition is correct. Okay, so that's an example of an actual transformation. Thanks for picking that up, Dan. Okay, let's go over here. So now I want to go back to the example that I was talking about in the first lecture. So this is relating a vector space to its dual. So let's define the following functions, or the following two functors, but I guess I'm going to do them one by one. So this goes from C vect to C vect, and V gets mapped to its double dual, and F V to W gets mapped to its double dual, and I'll remind you what that is during the proof of what I want to show. Okay, so then for any F from V to W, we have commutativity of this diagram, which is to say we have naturality of this map psi, which I define after. Okay, so I'm following my notes and I don't agree with the way that I wrote it. So let me put the pieces down and then I'll explain. Wow. Okay, so what we have is this map psi, right? And it maps V into its double dual by taking the vector V and maps it to its double dual like this. Now, that double dual can be defined in a couple of ways, I suppose. So, how do I want to do this? I feel like I'm not going to really use V double dual, which is why I've allowed myself to not define it. Okay, so let me write down the definition of F double star, because that's the important factor here. So F double star maps from V double star to W double star, right? V double star is the set of linear functionals on the set of linear functionals of V, right? So this map has to take in such a linear functional and then return back a linear functional on the set of linear functionals of W. So what that means is if you give me a linear functional, so this is a linear map from W to the complex numbers, this has to give back an element of the complex numbers. And what I can do is take psi and give it as input the composite phi after f. So that's the notation that I normally like, but we can use this notation as well. So to write the same thing again, given psi from V star to C and phi from W to C, we define F star star of phi. Yeah, is it? So, yep, from W star to C. Then F star star of psi of phi is equal to psi of phi of F. Okay. And then what I'm claiming is that this map, capital psi, is natural, which requires commutativity of this map. So what do we need to check? We need to say let V, an element of V, be arbitrary. We need the two different ways around this map, around this diagram, to be equal. So that amounts to capital psi W composed with F of V equals F star star of psi of V of V. Okay, and keep in mind that both the left and the right-hand side of this are elements of W star star, right? So what I need to say is, okay, I'm trying to get rid of this underline. So what we need to show is given phi from W star to C, we need capital psi of F of V of phi to equal F star star of psi V of V of phi. Okay, and maybe I'm standing in the way of that. So we can just perform a calculation. We calculate, and we get psi W of F of V of phi is equal to psi W of F of V of phi, which is equal to the evaluation at F of V of the functional phi, which is equal to phi of F of V. Okay, and then the other direction is F star star of psi V.
Did you skip over what V star star was before? Like
Yeah.
the evaluation just then, but
Yeah, that's where the evaluation is coming in from. So
Did you mean to make that explicit?
yeah, so let's say V, so I want to write it as, I call it phi, right? So phi from V to V star star is V maps to ev sub V, which goes from V star to C, and it takes in a linear functional, and it simply evaluates it at V. Yeah, you're right. I was meant to make that explicit. So earlier I was calling that thing V star star. Okay, and going to the other side of the calculation, we get this is F star star of evaluation at V of phi, and then we can just look at the formula that I wrote in red on the left board, and you see that this gives you evaluation at V of phi of F, which is equal to phi of F of V. So you can see that we got the same thing both times. So again, F star star of psi V equals psi W of F, and that establishes naturality. Okay, and let me get out of the way. Maybe I'll stop standing in front of the boards. Maybe, no promises. Okay, let's move over here. I guess I should ask, are there any questions?
I don't know what your plans are next, but given we've seen the definition of naturality and these two examples, but it still seems like with the definition of naturality, it kind of felt like, all right, here's this diagram to commute, and if it commutes, we call it natural. But I still feel like we haven't really motivated, okay, why do we care about this diagram commuting, and what's the sort of high level feeling I should get about two functors having a natural transformation between them.
Yeah, so that's a good question. There's a lot that you can kind of say about it, but I don't like a lot of the common sentences that you hear about it. So I've tried to set up this lecture without trying to argue that the mathematical concept of naturality is the appropriate formalism of what we would consider a colloquially natural map, as though it emerges from nature without human intervention or something. I don't think I have much to comment on with that. So I feel like this is a definition that we have. We are interested in it because it is part of the structure that might exist of certain maps that come up. And in particular, later when we look at adjoint functors, etc., that structure is going to crucially require the certain morphisms involved to be natural. And I think that adjunctions are pretty easy to motivate. They're like a real structure that exists, and you can see they can help writing with proofs, and they also give you relationships between different morphisms and different categories and things like this. So I don't think about the mathematical definition of naturality as, oh yeah, we've captured the concept of a naturally arising morphism. Does anybody in the audience have any comments on this? Because I don't think that I do, in fact.
Yeah. You could say it's a pretty sensible generalization of just the notion of being parametric in something. So if you say, if you change the point of view from, I want to map from a vector space to its double dual, to I want a map that somehow makes sense for vector space V as a kind of variable, then there's a question: to what extent is the thing you write down something that only works for a particular vector space, and in what sense is it something that works for any vector space. So you could be able to write down that's where the naturality comes in, right? It's a kind of agnosticism to the underlying object, and the only appropriate way to be agnostic to the underlying object in a category is to transform correctly when you change the object. And that's a morphism. So
yeah, that makes sense.
Like anytime, it's just a general pattern in mathematics where there's this kind of pervasive, even in Calc 1 when you're teaching students, there's this funny dance you do around, is this X on the page a variable? But now I want you to think about it as a particular number in this proof, right? It's like, suppose X is in R and has these properties, and then you say the sentence like, okay, in the rest of the proof, pretend it's an arbitrary but fixed X, whatever that means. There's all these sorts of funny sentences we use. And somehow in there, when you're talking about objects and not numbers, one of the ways of actually articulating what you mean is that the construction I'm about to do is natural in the sense that if I were to change the object, then I would in an appropriate way be able to change the map and everything else I'm doing. Like it kind of can be carried along that change. And that's a way of stating that what you're doing is not depending on the particular character of that individual object, but is somehow a generic construction. And I think that is capturing part of what we mean by natural. Yeah, it is always a little difficult to bridge the gap between this colloquial use of the term natural in mathematics and this particular formal use, and I don't think they're the same, but I also think it's not a bad choice of name.
Yeah. Okay.
I found that interesting, but I think I was less talking about like that gap you were just talking about at the end about between colloquial use and the meaning here, and more about I was hoping we could make more explicit. You were talking about like the sort of act of changing the object, and the F and G being compatible with that. I was hoping we could stare at the commutative diagram and the definition of natural transformation and sort of see why that expresses that idea, because I thought that was kind of like we just
Dan was getting at with parametricity, right? So I can let Dan answer for himself, but that's where, how can something be independent of the particular choice of object? Well, it's if we were to map across that object, we can still use the same map and get coherency. So the naturality square is saying, if you perform the map first, which shifts the object that is inside the... Oh, is that inside the right category? So, Dan, do you want to answer for yourself whilst I draw up this diagram?
Maybe I'll just walk back to that board and then you won't be able to hear me. Okay, so it's the third board. It's the second board back over there. I'll just click and open it, and you can do the same, I suppose.
We can just walk there.
All right, let's do it. Okay, so this one, right?
You could put out a personal board if you want to write next to it.
Yeah, I don't think I need to write.
Okay.
Okay, so it's kind of the question of when does a collection of maps deserve to be something in its own right? So these A to C's, you could just take a family of morphisms indexed by C, right? That's just a kind of thing. But then you want to perform it like an abstraction over that collection of morphisms. So the example Will just gave is a good one, right? So F in that case would be the identity functor on the category of vector spaces, and G sends a vector space to its double dual. And then you notice this pattern where you can, if you fix a vector space, you can define a map that sends vectors in that vector space to vectors in the double dual. And it feels like the way you write it down, it doesn't really depend on the structure of the vector space, right? You just need to know it's a vector space. And so in that sense, it feels natural. And what you mean by that is that family of linear transformations, that A to C for C any vector space, that family isn't just some family of random coexisting maps. Those are all brothers and sisters in some fraternity of conceptual unity, right? They're all one thing. And in what sense are they one thing? Well, if you were to transform any vector space to any other vector space, then they kind of fit together, right? So the A to C and the A to C prime, they make that diagram commute, which is a way of saying that any variation you can make in the vector space, that family kind of hangs together and is compatible with that variation. I think at this level of abstraction, there's nothing really more to be said, but there are many examples where you can, I suppose, one of the convincing examples is in the situation of representations of, say, a group. So a natural transformation, a special case of that is a morphism of group representations, a homomorphism. So many examples of homomorphisms that you know are actually examples of natural transformations if you set them up correctly. So I would say that the notion of a natural transformation in part can be justified because it's a generalization of the other notions of homomorphism of structured objects that we have, like representation.
Yeah, I'll make a quick comment. Something that clicked more for me just now is that you started with talking about the collection or talking about Ada. And I think I was implicitly thinking about it as like you start with F and G and you're like interested in this thing between them. But like, I don't know, the way you presented it then just kind of sounded like uh like Ada is the focus and then uh F and G sort of come along to witness like what's natural about Ada. So maybe you could, with the same map Ada, like starting with Ada, you then like find some F and some G, because especially when F is just like the identity functor, it seems I was like thinking these examples were like sort of uh hiding some of the complexity because one of them was just the identity functor. But I guess if we're more interested in Ada than F and G, then I think that made a lot more sense to me.
Yeah, I think that's true. So it's, of course, category theory was abstracted out of a large body of pre-existing mathematics, and generally in exactly that manner, where people noticed, we're not so much interested in sets or abelian groups as we are in homomorphisms between them often, right? So often there's a construction like mapping a vector to its double dual, or mapping between some Hom sets involving Hom and tensor, or 100 other things you might notice. And then, yeah, that's right, you find the functor and you find the category. So I think it's in maybe McLean's book, he says something like, categories only exist so that you can talk about functors, and functors only exist so that you can talk about natural transformations.
Right. If you start with a natural transformation, do you ever sort of end up with multiple choices for F and G, or is it typically just the one choice?
Funny question. Yeah, it's interesting.
Like, could you do like
you could certainly, yeah.
Double dual example? Can you do the double dual and the quadruple dual?
yeah, you could do that. I mean, you could come up with. Okay, so the example I was mentioning earlier, maybe I'll put that on this first board over here, just as if you don't mind, Will. So if I take C to be a one-object category, which has an endomorphism for every element G of a group, right? So take a group and then make a category has one object and the endomorphisms are just elements of the group. The multiplication is the composition. Then a functor from there to the category of vector spaces, say over C or any field, is the same data as a representation of that group. Now, suppose that every you could define a functor which, say, collapse some structure of that group. So you could have one functor that kind of maps to some quotient group H, and then this is a representation of H, and in which case the functor can't distinguish various elements of C, and using that you could come up with, you could have the same data of a natural transformation, the same functions being a natural transformation between two different functors. That's a somewhat artificial example, but yeah, you could do that. I don't know that it really conceptually means anything.
I was just sort of thinking more in, say, if we, like when you start with the sort of double dual natural transformation, like the functors aren't sort of written into it. Like you kind of have to figure out what the right functors are, right?
Yeah, that's right. In particular, it's not obvious that they're functors the way you write them down, right? You can care about the double dual without necessarily caring about F double star. And indeed, the first time you introduce it to an undergraduate, usually you don't stress the F double star because the naturality, in some sense, isn't needed immediately. The fact that that's a natural transformation, at some point it becomes extremely laborious and stupid to proceed without knowing that, because it just simplifies every argument you want to make about this construction, and to not use it would be kind of to willfully slow yourself down. But at the beginning it's not crucial, and maybe that's a general point you could make about categorical techniques. It's not that the first time you see any one of these natural transformations, it's like in the first 5 minutes absolutely essential you think about it by finding the functors and finding the categories and setting it all up like this. But soon enough you'll wish you had.
All right, cool. Forgive me for dragging us back here. I hope I haven't
No
cut it.
worries. All right, shall we head back to the other boards? Okay, so the other side of this would be to give a non-example, right? So what is not an example of a natural transformation? And I had the map between a vector space and its single dual, which in order to write down requires a particular choice of a basis for the vector space involved. So I was going to prove that this is not actual, but I'll push that to the exercises, and I'll just write down the map, and then we can talk about presenting mathematics. So let me kind of conclude this section with, on the other hand, we have capital phi sub v, which maps from v to v star. And what I need to do, let's assume for simplicity that this is a finite dimensional vector space. And let b be v1 up to vn a basis. Then really what I do is just map v to v star, but I can be a bit more instructive than that. So let v, so let's just expand v in terms of the basis that I just wrote down. So the sum from I equals 1 up to n of alpha I vi. So this become alpha I, an element of the complex numbers. Then if I let u be another element of v, then what is phi sub v of u, well, I need to expand u. I don't need to, but to make this clearer, I'm going to expand u in terms of the basis v as well. So that's from j equals 1 up to n. I'm going to call that beta j v sub j. And these beta j's are also elements of the complex numbers. Then phi sub v of u is equal to the sum I equals 1 up to n, sum j equals 1 up to n of alpha I beta j vi star of vj, where, if you recall, vi star of vj is equal to 1 if I is equal to j and it's equal to 0 otherwise. Okay. So that's a fair and square definition of a linear transformation. But what would it even mean for this to be natural? You realize kind of immediately it's a little bit strange because the star operator reverses the direction of the map, right? So given f from v to w, do we have commutativity of v mapping via f to w, mapping down phi w to w dual. And this is what I meant. The f single star swaps the direction of the map, right? But whatever, I'm not really that upset that the direction of the map swaps. I don't want a valid answer to like, oh, this is not natural. Look, like it's not even, we don't even get the same diagram that we would want. You can still go ahead and ask whether this diagram, maybe this would be of use to us, commutes or not. And the answer is no. So this thing doesn't commute in general. And the reason why is because we will need to pick a basis for W over here, and there's just no necessity for compatibility between the two bases, right? So going back to the left-hand side of the left-hand side board, we've got this part of the definition here, vi star of vj, and those elements vj are going to be mapped over by f at a certain point. In fact, it happens twice. And so we don't know that the basis elements of w are mapping to the basis elements of v. There's just no necessity for f to do that whatsoever. And so we're not going to be able to achieve commutativity even of this diagram, let alone anything else that can make this natural. Okay, so the answer is no.
Can you also say there are no natural transformations from V to V star?
Yes, this kind of goes back to your question, right? Like, this would be the one that you're interested in because this is, you would want F star to be this map that I've drawn down. So I don't know, but I think the answer is I don't care. Maybe
I think yes. The answer is yes, and that's a good exercise.
Okay.
To see that, yeah, it's kind of just showing that the obvious thing doesn't work is not really showing anything to be read. It's just kind of, there's no, what you've shown is there is no obvious, or the obvious thing in terms of choosing a basis doesn't work, but that leaves open the possibility that there's some deeper, more insightful construction which, in properly understood, relates V and V star. But
because it kind of doesn't it, like, it depends on what we're asking is natural or not. Because if we're asking if a particular transformation is natural, then we've answered that. But like now we're getting to like between V and V star, like is the idea of creating V star from V, like, can that be witnessed naturally by some transformation?
I think that question's a little ill-posed. So the functor that sends V to V, there is a functor that sends V to V star, so that construction is, in an appropriate sense, it's functorial, which is sort of a similar thing to naturality. If you change v, you'll change v star. But there's no relationship between v and v star that is sort of that needs nothing but the fact that v is a vector space. You need to know more about v in order to relate v to v star. And yeah, I would say it is. It's a good exercise to do.
So it's when you say needs more than just that it's a vector space, like, are you sort of alluding to that we don't have a basis for it necessarily, or like we need to pick a basis, and that's why it's not natural?
Well, I'm saying that a natural transformation is the only reasonable formalization of a construction of a vector in v star from a vector in v that knows nothing more than the fact that v is a vector space.
Okay.
Yeah, because couldn't you kind of answer this question stupidly? Like, can't you construct a new category of vector spaces paired with a choice of basis, and then you just give some terrible definition to the morphisms, like all of the bases are ordered and they have to map this basis element to that basis element.
Of course.
Can't you always do that? Can't you just do mega choices to make anything
Sure.
natural? That's what I meant by, like, it's not interesting. Like, yeah, you can do it, but
No, I think
it's not an achievement in itself. Like, you need to find some relevancy to the connection between V and V star that you've created, and you're probably not going to.
No, but you've changed the category at that point. I don't think it's as content free as you suggest. I mean, I misspoke earlier. Of course, there is a natural transformation between the identity functor and the dual functor. What is it?
Do you? Can you? I mean, again, I feel like I can do this trivially. Can I just?
Nothing clever. No changing the construction. I can always just send v to 0, right?
Yeah, could I also send v to negative v? Can I just do what I did?
No, negative v is not a vector in v star. No, I can send any vector v in v to a 0 vector in v star, and that will be natural. But yeah, apart from that, there are no other ones.
Yeah, so this is what I mean. Like, you end up doing other math in order to justify that what you've written down is deep, right? Like, that's not really.
I mean, there's another perspective from which this looks like it's more contentful, the fact that there is no non-zero natural transformation. We don't want to get too off track, I suppose, but when you sort of zoom out to the, like, what is a vector space, right? I mean, what kind of gadget is that? And you can talk about the kind of category that the category of vector spaces is and the kind of structure it has. And there's another lens on the nature of this kind of mathematical object, which puts the notion of dual and kind of the way in which, for example, finite dimensional vector spaces are related to their duals more centrally than the structure of a vector space itself. And then the existence or not of natural transformations between various combinations of these central functors starts to move closer to the center of your attention and becomes more meaningful once you kind of center that point of view, which starts from the category and kind of looks in rather than starting at the objects and looking out.
Right. Okay. So shall we move to the next set of boards and talk about talking?
Yep.
Okay. So presenting mathematics. Okay, so I'm no expert, but at this point I've got a little bit of experience, and I've certainly spoken to a lot of people about it, but I want the style of this part of the lecture to be a bit different. I'm not going to be educating you on facts about the universe. We can make this more discussional and we can draw up some dot points, but I've already got some main ones that I wanted to write down. So the first one that I wanted to say is you can think about structuring a lecture, a self-enclosed lecture. So if you're going to introduce a point, make a point, and then conclude in one lecture, and it's not going to be a series, then you can just think about it like an essay. So present like an essay. That's at least going to be a good starting point for getting into formal presentations to begin with, right? So what do essays have? Well, I guess essays normally have a title, but you go ahead and put a title to your talk if you're so inspired to. And then you have your introduction. And here you're allowed to speak vaguely and imprecisely, but not incorrectly, right? So that's an important distinction to make. So in general, loose speaking inside a lecture is perfectly fine. Vague speaking is also perfectly fine, but incorrect is not okay, all right? And I'm going to talk about this point a lot, but I think that's very important. And when you're talking loosely or when you're talking vaguely, you want to have a reason why you're doing that. And you also want to have a consciousness whilst you're doing that. You don't want to be accidentally speaking loosely when you're halfway through a proof or speaking vaguely because you're a little bit unsure of what you're talking about. That's not the point. The point is that sometimes it is helpful to not talk with exactness in your speech, because it can give the idea, you can sometimes give the idea better by talking a little bit loosely or vaguely, but you have to be careful not to sacrifice correctness whilst you're doing that. Okay, and then inside the body, you want to have some kind of detailed element. I think it's personally a bit frustrating when there's only vague, high level, when the whole lecture sounds like an introduction. That can be a little bit of a waste of time, to be totally honest. So details, make your points, make your point precisely. I think that one thing that's really beautiful about math is the fact that you don't have to argue and convince the listener of your perspective and your opinion right up until they submit and decide that you're correct. You can actually just let the math do the talking, right? And that can sometimes be hard to do, and that's part of the skill of presenting mathematics. You want to know how to use mathematics to reveal itself, because mathematicians are much more convinced by the mathematics than by any, poetic, artistic argument that you can make about the mathematics. So here I'd say something like, let the math do the talking.
If you don't mind me adding a detail here, I think it's partly there's no substitute for processing it yourself, right? So my general feeling when I hear people trying to tell me their understanding of the math and not just give me the math is, firstly, what makes you think you understand it better than I will if you just tell me the thing? Tell me the thing, and then you can give me your version. But maybe I think I'll get it better or differently, and I don't want you to get in the way. So just serve it up to me, please. I think a lot of people feel that way.
Yeah, for sure. Okay, so imagine how frustrating reading fantasy would be if the author would come in and every now and then convince you of what these metaphors and magical elements of the universe are meant to be. It's kind of like, just give me the story, right? So yeah, trust that the audience is capable of hosting and creating an imaginative landscape inside their head, and they can process the information on their own and also allow the audience to ask questions. So they'll develop their own perspective, and then they can ask you a question and see how it maps onto yours, and that can be a healthy part of the discussion. So yeah, math is a rigorous sport, and you have the opportunity to offer that. So show some sympathy and offer it. Okay. We learn math by examples. I don't care how abstract and complex your hero mathematician that you look up to is. We understand mathematics by examples. So examples are incredibly important. And what lots and lots of people who attend math seminars do is they hope to get a beacon of light out of the idea of what you're saying. And sometimes it can be tempting to think that abstract, complex mathematicians will just read the general theory and immediately it will all click into place. I'm certain there are people that can do that, but to the most of us, you get an example and then that implies an idea, and then you can let that example parameterize the abstraction whilst you're learning it. Okay, so the example can also go before the details and the abstract theory and the making a point. That's kind of part of the art of it. You'll find as you present more mathematics that there are that sometimes you just want to give the general story and then the examples, and other times it's the opposite way around, where you're like, let's look at these things and notice that something is up, right? And then we're going to go in and explore. So that's like writing music for a film or something. There's no template for the way that the music should accompany the story. But depending on what is happening in the film, you might decide to balance your motives and your ideas differently. So that's a little bit case by case, and that's a little bit up to the artist. But having no examples in any of your talks is probably not going to lead you to be a very good presenter of mathematics. So definitely always be asking yourself, how can I put examples, and also meaningful examples, right? Like Dan said, the zero natural transformation exists, but Jesus, imagine if I gave that as our example of natural transformation. Okay, and then
what does it feel like if there are too many examples? Not that happens very often, but
oh yeah, that's true. Then it doesn't feel like there's a theory, right? So I'm not sure if I've seen so many instances of too many examples, but it seems confusing. It's like, what is the point? Where are we relating this? Did you have something more pointed that you wanted to say about that?
I don't know. I'm just trying to think if I've ever sat there feeling I've seen too many examples, which suggests that you can probably not go wrong by putting one more example than you think is necessary.
That's true.
But I guess it probably feels a bit like, get to the point already.
Yeah.
You have to be conscious of the time limit, right? So while in principle, more examples might always be better if you had infinite time and the attention of your audience was also infinite, you do have to get to the punchline, and that dictates maybe one example or two and not 10.
A factor in that is also how you define more examples, because if you're like often you have like indexed families of examples where like one whole collection that you could parameterize in some way is really the same idea, but you're just like seeing it like it's almost identically the same idea, and you're just like lazily like instantiating it like
that subject is called linear algebra. That's right. Let's do another matrix today.
Like if you could genuinely come up with more and more examples that are genuinely a different idea, but it's like yet another example, I think that's just like even more illuminating. But like I guess you kind of always eventually run out, depending on how like rich the idea is.
Yeah, for sure. And I would say that non-examples are sometimes really helpful as well. And I sometimes think that people don't put enough of these in. So a good example of that would be like category theory, right? You introduce category theory and it's easy to give a million different examples, but why don't you give me something that's not an example? It's actually not so easy.
Yeah, let's fight about this. This is a good one. I am not a fan of definition topological space, and then the next 15 minutes are things that aren't topological spaces. When someone does that to me, I'm sort of like, Well, if I wanted to take the non-topological space class, I'd go do that. I mean, okay.
Yeah.
I get it. Yeah, I get why you want to talk about counterexamples, but this style of mathematics where everything has counterexamples attached to it, I'm supposed to care about them. I really don't
So
buy
it's not
that.
to care about them, I would say. So it's to help you know what is the thing, right? So when you're say continuity, right? If I'm like, this is continuous, this is continuous, this is continuous, then maybe you're like, okay, but I don't get it. And then you see a discontinuous function, and you see a really blatant graph of a discontinuous function, and then you're like, that is not continuous. So it's not to help me understand discontinuous functions. It's in fact to help me understand continuous functions.
I think that's
right?
a very good example of where non-examples are useful, but that's not maybe the generic situation. So more often non-examples take the form of, I mean, there you have a natural class of things, functions, or, some restriction on the functions, integrable or something. And then within that you have continuous, and you point out something within the bigger natural class, but that is not in the subclass of the things you're talking about. But there's this kind of artificial non-example where you just kind of break the thing, and then you're like, hey, look, I broke the thing. And then your audience is like, okay, you broke the thing. Well, that's good.
So I fully agree. I hate that. I despise it, right? And I think that it comes from an over romanticization of the concept by the speaker. So say you're talking about topological spaces and you've been completely convinced of them, right? And you're one of these internally geometric creatures, and you just love thinking about the sphere, and you love thinking about the torus. And even better if it's like a 5 torus or something that you can't even visualize, but you've somehow gotten your head around it and you've fallen in love with it, etc. I think it's really fun in those instances to be like, it's almost like I love it so much that I love breaking it. It's like, oh, but the point with the line with two origins, that's not a manifold. Like, let me show you this clever thing that it obstructs, right? And that's almost like putting your annoying passion into it. So I think that this is a really important part of math talks. You can fall so in love with something that you find even the most what's the word? Like really edge case non-examples completely entertaining, right? And so you're excited to present it because it just made you laugh when you first saw it, and made you feel happy when you were first exploring it. But that stuff is infuriating. That's like the over excited actor or something, like the actor that overacts. It's actually infuriating, and you can see that they're having tons of fun. So I could put a point here. I say this to people about music, and I think it's really relevant in mathematics sometimes. The performance, let's call it, is not for you. Okay? And I'm sorry if that hurts, but I think that this is so goddamn important. If you are the performer, you are the least important person in the room. Okay? The performance is not for you. And if the person in the room during the performance who is having the most fun and who is getting the most out of it is you, then your performance sucks, right? You are the one in the spotlight, and you're the one that people are watching, but it's not for you. It's not to have the attention on you, and it's not for you to come and feel your passion, and for you to uh, get meaning out of life inside that moment. You're actually there for them, right? And keep that in your mind at all times. So that probably involves cutting out your most favorite bit, right? I mean, another example would be number theory or something. I am positive that there are number theorists out there that have absolutely fallen in love with the most ridiculous integer relations that you could possibly imagine, and they're so desperate to tell you about it. But too bad. This is a talk about cryptography. It's irrelevant. You know what I mean? So I think that that's really important. Okay, some of the other dot points that I had, so the kind of golden rules, I suppose. This is one that I emphasize a lot. Don't try to be interesting. Now, I have not said don't be interesting. I have not said don't enjoy it, don't be passionate, don't have fun, don't feel excited by what you're presenting. don't look forward to it. Don't, I'm not saying anything like that. I'm saying don't put active effort into trying to be interesting, right? So I know one of Dan's favorite points, and being a student of his, I suppose I've adopted as well. It's not our job. It's not our job to entertain. Now, Dan and I do have discussions about this word, but I believe that there's a lot of depth inside the concept of entertainment. I think that you can even use entertainment in order to enlighten, right? But I think maybe somebody like, by all means, speak for yourself, Dan, but the concept of enlightenment can sometimes involve entertainment for pedagogical purposes, etc. So yeah, there are edge cases here, but as a general rule, it's not our job to sit there and leave the crowd entertained, right? Instead, our job is to enlighten, and there is just math that's really boring, or a better word would be grueling. Like there are 20 case arguments. There are nested inductions in math, and sometimes you just need to go through them.
Yeah, before you go on, maybe it's an interesting point. I think it's not like I object to being entertaining, and I think it's actually to some extent an ideal, but there's a hierarchy of ideals here, right? And enlightenment and clarity comes first, and it's so hard that you listening, you won't achieve it, right? So you will try your whole career to just be enlightening and clear, and that's fine, right? And then it's like, if you master that and you're one of the most brilliant lecturers and you're very clear, then you can reach for this goal, which is entertainment on top of enlightenment. And that's amazing. But I think that people, what more often happens is the harder thing is, like, you kind of distract yourself from it by substituting this easier thing that you also think is an ideal. So it's so much work to just be clear. It would be so much easier if I could just get away with being entertaining instead in this little bit. And then I'll buy myself out of this obligation to be clear and actually enlighten the audience on this difficult point. So that it's not like I would say never be entertaining or try to be entertaining. A kind of stupid flourish that makes the audience smile is sometimes just the right thing to do, right? But it's I think to the extent it's a get out of jail free card. If being enlightening is being in jail, you know what I mean? Then it's a bad idea.
So I'll say that I'm aiming for beginners here, by the way. So this is kind of a talk for people that are wanting to get into math presentation that maybe haven't done it so much. Yeah, for sure. There's the expert level, and maybe being entertaining is part of it. I don't know. I wouldn't even say that I'm there yet. So yeah, speaking of the hierarchy, I guess that's a good opportunity for the next golden rule. This one stings a little bit, but it's true, and I've already abused it even in today's lecture. Correctness matters. So I was lucky to have a polite member of the audience that politely corrected me, and we worked it out, and it was an opportunity of learning. That's fine. It is our job to enlighten, and also we are scientists, and as scientists, we are trusted by society in order to get things correct, right? And this is worth writing on the board because it will motivate you to be more humble with what you say, right? So a few ways that you can achieve higher correctness. One easy one is say less. And that's a surprisingly impactful one. So a lot of the time the audience are writing notes, or they're thinking about what you've said, or they're mapping it onto what they already know. You can do just concrete silences for even a minute, and it will feel like a lifetime whilst you're the presenter, but it's not a lifetime for the audience. And if you do that more, you're going to have an easier time at getting through a full lecture only saying correct things. And that's a very good initial goal to start off with. So if you give, as your first math presentation, a slow, boring, correct talk, I think that's pretty good. And I think that's a great place to start. And then once you're really nailing the presentation of the technical elements of a talk, then you can build up things like pace and context and swapping between loose speaking and precise speaking, etc. This also requires a lot of practice.
What part do you think requires practice rather than just preparation? So, of course, thorough preparation is part of just saying correct things, but I agree, it's not only that. There's some element that requires practice on top of the preparation, so I'm interested in why you chose this
doing it
word.
with eyes on you, man, like that is just such a different experience. It's the same as if I think that's more general for any live act where you're in front of people. So it's one thing to do it, it's another thing to do it with.
So, seminar on presenting mathematics, and you just disappear. It's true.
Yeah, don't cease to exist.
Yeah, that's right. That's for don't die. Yeah, don't die.
What's the worst that could happen while you're presenting?
That was really good. I saw some points in the chat. Oh, I see. Okay.
Are they just trying to make a point about silence?
Yeah, that's right. Yeah, exactly. I'll give you some time to think and walk out of the room. I've never tried that before. Just put the chalk down. Say, you guys look confused. I'll come back in a minute and walk out. Yeah, it could be useful. I've never actually done that in a lecture or a talk. Just kind of stopped for a full minute. I mean, I've probably stood there for a minute thinking about a question, or the most horrible thing that happens in a lecture where you hit a point where what you prepared is wrong and you need to fix it live. That's not pleasant. I've probably stood there thinking for a full minute in that circumstance, but I don't know. I think I'm often sitting there thinking that I can't keep up and I'm a little bit lost and wishing I had some more time to think. But if the lecturer actually gave it to me, I might flip to thinking something like, hey, what are you doing, man? You're wasting my time. Keep going.
Yeah, I think even in situations where I'm thinking, I'll still like constantly say, oh, I'm just thinking, give me a sec. Just because the silence is hard to handle.
It's actually quite rare in my experience that you're thinking and then you'll catch up. It's sort of, I'm either with you the whole way, or I'm with you and then I lost you and I stay lost. It's actually really hard to be lost, catch up live, and then without any skips in comprehension, right? I mean, sometimes you just kind of like, okay, well, that part I don't get, I'll come back to it later. But it's
yeah, that's usually more likely in my experience.
Yeah.
Yeah.
Which is fine. And often the first time you hear a lecture or a talk is more like getting a sense of where the tricky bits are, right? That's sort of which bits when I was listening did I just not follow, and then you have a sense of, okay, well, that's where something probably happened. There's something there. It's not.
I'm worried that Will didn't notice that his laptop account timed out. He usually keeps it in another window, but
yeah, okay. His iPad account's back.
Okay. I wonder how long he was talking.
Yeah, we should really do that audio cue.
Yes, I know exactly what you're talking about, and yeah, you should. I don't know how much you can hear through my iPad when I get disconnected from my computer, but not my iPad.
Nothing.
Is the answer nothing? Yeah, okay. All right, so I was probably gone for ages there and I didn't realize. So I didn't really say much more. I was very confused why nobody was talking, and I thought maybe don't die. But like, don't die. So don't say so much.
Wait. So you were speaking and you saw somebody write up "Don't die."
Yeah, but yeah. And so I was like, I was talking about getting correctness. And
Everybody was completely silent, and somebody wrote up "Don't die." That's an experience.
The amount of times that's happened to me, I'm really sure about that. Whatever. Okay, let me conclude, and then we can call it a day. So we'll talk more about talking later. But Billy and I would like to encourage anybody and everybody to do a Shadows of Computation presentation. So we are offering the opportunity for you all to do like 20-minute talks on anything that you're interested in. Or that can be half an hour, that can be an hour, whatever you're confident to do. But we've prepared a few sample topics. You can see them in the tutorial sheet for this week. And we will also work with you to help you set up a presentation and find a topic that's interesting and get you feeling like you are confident to present an idea. But we kind of just wanted to suggest this to give people an opportunity, an easy introduction to talking. So rather than maybe starting off with an hour-long seminar talk inside MetaUni or in front of a blackboard with people in the audience, you can just do a simple talk here with the aid of Billy and I helping you get prepared for that. So we offer you to present in Shadows of Computation. We will help you. We have topic suggestions, see tutorial sheet, and we will offer feedback on the presentation itself. And I mean, I guess I haven't asked him yet, but Dan, I'm sure you'd be happy to offer some feedback as well. Is that right? Okay, great. So yeah, this is a group of people that have done a number of presentations now, particularly in MetaUni. So we would be willing to help you. We're willing to help you over the psychological hurdles as well. We know it can be an anxious experience to begin with, and it can be scary. We can help you with that. We'll help you with the topics. We'll provide feedback at the end. So if this is something that you are interested in doing, please do and talk to us about it. Yeah. And maybe we can do some weird tech cool thing as well. But I think that's not great to focus on for people whose first time it is presenting. But maybe a goal for Billy, Dan, and I would be that we all give a talk each involving some experimental technology or something. Could be kind of cool. Okay, nice. Is that Riley? I think it is, right? Riley, definitely.
I don't know if you can hear me. Yes.
Okay. Okay, sweet. So let's communicate about it. By all means, just send me a private Discord message if you want, or post on Shadows of Computation, or like talk to us at the end of one of these lectures. Like whatever you want to do, any means by which you want to communicate with us, just go ahead and do so, and we'll get you set up on that. Okay, I think that's today's lecture. We'll end it there, and next time we'll talk about something different.
Awesome. Thanks.
No worries. Thanks, mate.
When you say experimental technology, you're talking about replays, right?
Yeah, so replays or VR. I'd very much like to try VR or whatever other idea we have.
Yeah, let's not underestimate just throwing some funny object in the world that rolls around or does some cheap and easy thing as well.
Yeah, even something small. I just mean like, whilst everybody else is going out on a limb and doing their first math presentations, we could match that by also going out on a limb and making it the first that we did something that we're maybe not fully experienced in doing. But I'm sure that all three of us. What was that? Sorry.
First math talk as a tree.
I know that you've been dying to do that.
Finally, I've got my excuse.
Yeah, let's see if you can relate it to the talk somehow. If you can make that relevant, I'd be very impressed.
I want to thank both Billy and Will for including this segment on giving talks and taking the initiative to have this idea as well. I do think it's an underappreciated aspect of mathematical culture. We don't talk about it enough. It's implicit, and we give a lot of seminar talks to each other, and people emphasize it as, often in the context of applying for jobs, you need to give a good talk, or people will think you're a crazy person or that you don't know what you're talking about. But it's one of the central human rituals of being a mathematician. It's really important, and I think it's great to talk more explicitly about it, and to those who have had a lot of experience to try and pass that on. So thanks a lot, Will. I know it's not always easy to stand up and give advice when sometimes you feel like nobody lives up to the advice that they give to other people entirely, right? That's impossible. But it's still important to do it and not be like too modest about it to say, well, maybe I'm not perfect, but here are some things I've learned painfully, often by watching myself do these terribly stupid things over and over.
Yeah, no, you're completely welcome. So I was kind of inspired by, there's a really great YouTube channel called Chess Vibes, and he's a guy that talks about chess. And his videos are brilliant, and he's not a grandmaster. And I actually respect this so much, He's just a guy that's on his path to becoming a grandmaster, and he's incredibly passionate, and he just talks about things that he's learned along the way. And he'll sometimes have videos of like, 2 years ago, I presented this idea, but I'll totally think about it differently now. Like, I've had this realization kind of thing. And another person who I think has interesting comments on this is Bo Burnham. If you know him, he's a comedian. He talks about, in the modern era, everybody has to become who they are publicly. It's not really like an option anymore to be completely silent and then one day fantastic. Like, people develop on YouTube and you can see their full path. That's kind of the future, and I'm really into that idea. So I like the idea of being like, I'm on the path of becoming as great of a math presenter as I possibly can, and this is where I am, and this is what I've learned, and I'm encouraging others to come with me, and I'm excited to grow, and I'm willing to do that publicly. I think that's a really healthy message to give to people, especially young people nowadays. And so, like, you've got to put yourself out there first if you're going to, who was it, Gandhi? You've got to be the change you want to see in the world.
Yeah, I'm not even sure one way to hear that message is to be thinking that you need an audience for the audience to give you feedback, and that's true perhaps, but my own experience is just the first time I recorded and watched myself lecture, I picked up 10 things which I guess in retrospect I'd been doing for years, which I found quite annoying. For example, saying like all the time, or 20 other things that you could pick up if you go and watch a lecture of yourself. And you just have to do that a few times and you'll fix a lot of those things, or you'll start to. And you can become much more eloquent in public. You don't even really need, it's helpful to have people give you feedback or to point at things that, maybe you're not quite willing to look at because you feel a bit, not ashamed, but you may have habits that to fix them would require a lot of effort, and you're sort of hiding them from yourself, and these kinds of difficult things. But there are lots more superficial things that you can fix very easily with a little bit of practice that you'll notice the first time you actually just listen to yourself speak. So I'm a proponent of recording talks, especially, and even especially for people just starting. It doesn't have to be publicly shared, but if you just watch yourself speak, this is of immense value.
Yeah, it's invaluable, for sure. Okay, shall we leave it there for today?
Yeah, thanks, Will. Thanks, everyone.
No. Thanks for coming. I'll see you all next time.
If anyone wants to
Thanks, guys.
stay. Thanks
I
for-
need to get a day of work, I think, so I'll head off. But yeah, see ya.
Alright, see you.